Hello and welcome to the fourth and final video for the FP3 chapter, Further Coordinate Systems. As usual, starter on the screen here, this is to review FP1 work on rectangular hyperbola. Pause the video now if you've got time, and I'm going to go through the answer. So the point P, where x equals 2, lies on a rectangular hyperbola with this equation. And we want to find the equation of the tangent t. But before I do that, I'm going to put x equals 2 into the equation to find the corresponding y coordinate. So our point P has coordinates 2, 4. Now to find the equation of the tangent, I do the same thing I always do. I differentiate the equation, plug in the numbers for the coordinate to find the gradient, and then use my line equation. So to differentiate this, I'm going to use implicit differentiation. We need to use the product rule as well. So if we differentiate x and we leave y alone, we get 1y. And then we have to leave x alone and differentiate y, which is dy by dx. And on the right, differentiate 8 to give 0. So dy by dx is equal to minus y over x. And at this particular point, where y is 4 and x is 2, that gives us a minus 2 as our gradient in the line equation. So y minus y1, which is 4, is equal to m minus 2 times x minus x1, which is 2. And we can expand that out if we want to give a final equation as y equals minus 2x plus 8. And there is the equation of the tangent. A quick note that rectangular hyperbolae are a very specific type of hyperbola. They are hyperbola with perpendicular asymptotes. In addition to this, the foci are not on the x-axis as is usual. If you were to plot these, you get this. And the x-y axes are your asymptotes, and the foci are here, and the directrices that we talked about are like this. So they're a little bit different to what we normally talk about in FP3, but fortunately we don't need to worry too much about rotating the diagrams or the foci or directrices or anything like that. We just end up with a much reduced equation here. So that's a little bit of review for FP1. In this video we're going to look at loci, putting together everything we've learned so far to solve some problem-solving sorts of questions. Two examples, one fairly quick and one quite involved. Just a quick reminder that a locus of points is a set of points that satisfy some constraint or rule. We've already done this with the ellipses and hyperbolas themselves, defining them as loci, but there are also lots of other loci that you might be asked to find. For example, the tangent to the ellipse with the equation this, the general equation at the point P, general point, crosses the x-axis at A and the y-axis at B. Find an equation for the locus of the midpoint of AB as P moves around the ellipse. So I'm going to just borrow the equation for the tangent to the ellipse from the first video so that I don't use too much time going through that again, and we can get to the new part of this question. So here's the equation for the tangent to the ellipse. Now let's have a look at what is going on here. Here we have our general ellipse. We don't know any specific numbers, but that's okay. As P moves around the ellipse, the tangent changes. So the point here is not the point on the ellipse. This is the midpoint between where the tangent crosses the x-axis and the y-axis. So P is about here. The tangent is touching the ellipse at P, and to get the midpoint we go halfway up the y-coordinate for B and halfway along the x-coordinate for A. And the question is, what is the locus of the midpoint as P moves around the ellipse? So as P moves over here, the tangent becomes horizontal. And as P moves this way, the tangent goes like this. As it continues around, eventually here it's vertical. As it moves round, tangent moves down here, and then horizontal at the bottom. In this quadrant it's positive again, and on the far right it's another vertical line, and then it comes back around and repeats. So as the tangent changes, obviously the midpoint changes. If P is here, the tangent becomes a longer line from axis to axis, and the midpoint comes out a little bit further. But what is the locus of that, and what is the equation? So initially the question might seem quite difficult, because although their motion is connected, it's quite different movement, the movement of P around compared to the movement of the midpoint M. So let's get stuck into this. What do we know? I've already got the tangent to the ellipse, so I know the equation of this line using the methods in the first video. We can also find the coordinates of A and B. We know the coordinates of A happen when y is equal to 0. And if I put that into this equation up here, we get bx cosine t is equal to ab, so x is equal to a over cosine of t. Similarly, for point B, we know that happens when x is equal to 0. Put that into the equation at the top, and we get ay sine t is equal to ab, which gives us y is equal to b over sine t. So we've got the coordinates of A and B. To get the coordinate of the midpoint, we need to go halfway from 0 to the x-coordinate of A to get the x-coordinate of M. So the x-coordinate of A plus 0 divided by 2 is just half of this. So for M, the x-coordinate is A over 2 cosine t. And in the same way, the midpoint from the x-axis to B is half of B's y-coordinate. Because we do this plus 0 divided by 2 gives us B over 2 sine t. So by finding the equation of the tangent, substituting in the points we know to get the coordinates that we don't yet know, we can then find the midpoint coordinates. Now, this is the interesting part of this question. Changing the coordinates of M, which are dependent on a parameter t, which of course will change as P changes. A and B are fixed for whichever specific ellipse we've got, but T is not fixed. So as T changes so that P moves around the ellipse, T changes here and M moves as well. So how do we turn this general coordinate for M into an equation? And we do that by introducing x and y. But we have to be a little bit careful because we're already using x and y as coordinates for a general point in the equation for the ellipse. So I'm going to use capital X. And I know capital X, the x-coordinate of M, depends on t, so I'm going to make an equation with that coordinate. And capital Y is going to be the equation for the y-coordinate. And then to combine these, we do a sneaky little trick. We rearrange to make cosine t and sine t the subject of these. We get b over 2y, a over 2x, and then we can use the identity sine squared plus cosine squared equals 1, because sine squared t is b over 2y squared, and cosine squared t is a over 2x squared, and they must equal 1. So I get b squared over 4y plus a squared over 4x is equal to 1, and that is the equation for this set of coordinates as they change with t. So this is the equation of the locus of points for the midpoint of AB as P moves around the ellipse. And the idea here of turning these into mini equations with x and y, capital X and capital Y, is quite a common idea in these loci questions. It can be quite difficult to understand how this is all working together on the graph and how M actually moves, so I'm going to switch over to a graphing app and show you what this looks like. In order to do this, I've had to put in numbers for A and B so that we actually have an ellipse that I can talk about. So I've chosen 5 and 2 at random here. And then we have the equation of our tangent, and as t moves, you can see that tangent moves around, because as t changes, the point P is changing. And then I've put in the points A, where that crosses the x-axis, B where it crosses the y-axis, and again as t changes, A and B change. Then the midpoint of those two with the coordinates that we had written on the previous screen. I'll just let that play for a bit, and you can see of course that there are points where there is no midpoint, where the tangent line is parallel to the x-axis or parallel to the y-axis. And as that's moving around, I will put on the final equation that we had for M, and you can see that it tracks with this equation. And of course the asymptotes for this graph are due to this point where it's vertical, this point where it's horizontal, and so on for the other two as well. So this is the sort of question you might get with a locus question. This second example is a bit longer, it's quite involved, and there are a couple of sneaky tricks that you need to be aware of as we go through that are useful to remember for other problems like this. So we've got the question here, the normal at this point and the normal at this point to a parabola with this equation meet at R. So the two normals intersect at the point R. So it's important to realize that R is not on the parabola. Find the coordinates of R. And then we've got two more sections here. I'm going to go step by step, but I'll quickly read through it. The chord PQ passes through the focus of the parabola. So joining P to Q goes through the focus. And we need to use that to show that PQ equals -1. And then we're going to show the locus of R is a parabola with this equation, and that's very similar, the idea of this question is very similar to the previous example. So let's start off with the coordinates of R. I'm going to do these one on each screen because there's quite a lot of space needed for each one. Now you found tangents and normals to parabolas in FP1, but that was a long time ago, so I won't take the general result, I will go through the process. I'm going to do implicit differentiation, so we get 2y dy by dx is equal to 4a. So dy by dx is equal to 2a over y, and at the given point I'm going to use p. The gradient at p is equal to 2a over the y-coordinate of p, which is 2ap, so that gives me 1 over p. For the gradient of the tangent at P. Of course, the gradient for the tangent at Q, because the only difference here is that the P has changed to a Q, these are both general points, so it would be 1 over Q. And I'm not going to do a separate equation for this one, I'm going to go all the way through, find the normal for P, and then just change the P's to Q's, and that will be the normal for Q. But because it is a normal and not a tangent, that tells me that the gradient I want is minus P. And if I put that into my line equation, I get y minus y1, which is 2ap, is equal to m minus p times x minus x1, which is ap squared. Now that is y is equal to minus px plus ap cubed plus 2ap. And as I said, that's exactly the same for q, just replacing all of the p's with q's. We don't need to do the work twice. So I've got the normal at p. and the normal at Q. Where they meet is where this is equal to this. So I need to combine these two equations in order to get the coordinates for x and y. In this case, I'm going to put them equal to each other. Get minus px plus ap cubed plus 2ap is equal to minus qx plus aq cubed plus 2aq. I'm going to gather the x's and factorize to get a q minus p here, and everything else I'll put on the other side. So we've got a q cubed, and from the left minus ap cubed, so factorizing that gives me this. And then we have a plus 2aq, and from the left a minus 2ap, so I'll factorize that as well. So rearranging and factorizing at the same time gives me this. And here is the first of our very sneaky tricks. This is not likely to be something that will occur to you unless you've seen it before. But after you've seen it in this example, you should remember it for subsequent questions. Q cubed minus p cubed can be written as q minus p times q squared plus pq plus p squared. And I'm sure you can convince yourself very quickly that that's true by expanding this out. And the reason that's useful here is because that gives each of my terms q minus p, q minus p, q minus p. So I can cancel those in the next go. So we've got a q minus p, q squared plus pq plus p squared plus 2a q minus p, and as I said, we do that so that these can cancel. And that gives us x is equal to a q squared plus pq plus p squared plus 2a. And that's as simple as we can make that for now. So that's the x coordinate. But we also need the y coordinate. So we're going to have to put this back into one of these two equations. It doesn't matter which one. I will put it back into the p equation. So substituting x back into here, we get y is equal to minus p times x, which is a q squared plus pq plus p squared plus 2a, and then from the y equation we also have plus ap cubed plus 2ap. Now I should try and simplify this a little bit if I can, so I'm going to expand everything out and see if that helps. We're going to have a minus p times a times q squared minus a times p squared q minus a times p cubed and minus 2ap, and we still have plus ap cubed and plus 2ap. So that did help because this will cancel with this, and my minus ap cubed plus ap cubed will cancel as well. So that simplifies quite nicely. Minus ap q plus p. So after a reasonable amount of work, we've got the x coordinate of r a q squared plus pq plus p squared plus 2a, and the y coordinate minus ap q plus p. That is the first part of the question done, with a very important sneaky trick to remember here. So the second part of the question says the chord PQ passes through the focus A0 of the parabola. Show that PQ equals minus 1. And I've put up our R coordinates here from the first part of the question in case we need that. So what we need to do here is get the chord PQ. We do that in the usual way. We've got the coordinates here. We can do y2 minus y1 over x2 minus x1 and put that into the line equation. Then we know it must go through this point, so we can substitute these into that, and hopefully along the way we will find this must be true. So let's go for it. The gradient 2a q minus 2ap is this, divided by a q squared minus p squared is this. And here we can apply another sneaky trick, one that you should be more familiar with, because in the denominator there we have the difference of two squares. So we're going to have q minus p, q plus p. So not only the a, but also this bracket can cancel, gives us 2 over q plus p for the gradient of this chord. So the chord then has equation y minus y1, and it doesn't matter which one, let me use the p coordinate, is equal to m, 2 over q plus p, times x minus x1ap squared. And on this line we must have the point a0. So if I substitute those in, let's see what we get. The y coordinate is 0, which gives us minus 2ap on the left, and the x coordinate is a, which gives us a minus ap squared on the right. So if I multiply everything by q plus p to get rid of that fraction, we get this. If I expand the bracket as well, there we go, which gives us minus 2apq minus 2ap squared equals 2a minus 2ap squared. These two cancel, and we are left with minus 2apq equals 2a, and you can see here that tells us pq equals minus 1. So part B is finished. We know that PQ does indeed equal minus 1. Putting that together with the coordinates we have for R up here, we're going to use both of these together to help us to show that the locus of R is a parabola with this equation. We're going to do that, first of all, by replacing PQ in here, this one in the middle, and here with minus 1. And then we'll do more or less what we did in the last example, where we're going to turn this into an x equals equation, this into a y equals equation, and hopefully we will be able to combine them into a single equation that matches what we've been given in the question. So first of all, we've got x, and I'll use capital X just to distinguish it from this x here, but at the very end I will change it into small x and y to match this. So capital X is equal to a p squared plus pq, which is a minus 1, plus q squared plus 2a, and y is equal to minus a pq, but the pq is a minus 1, so that's a plus a p plus q. And here we're going to use our final sneaky trick, and that is that p squared plus q squared comes from squaring p plus q if you subtract 2pq. So we're going to replace our p squared plus q squared with p plus q squared minus 2pq in here. We still have a minus 1, that's okay, but I'm trying to get p plus q in a bracket because we have p plus q in a bracket here, and once we've got p plus q in both, we should be able to substitute out to get x and y in the same equation. So this x coordinate is going to change to a. Let me make it really explicit what I'm doing. So I'm going to change that p squared plus q squared into a p plus q squared minus 2pq. But we still know that pq is minus 1, so actually let me change that into a plus 2, and then we have a minus 1 still from the coordinate plus 2a. So if I combine those two numbers and expand out the bracket, we have a p plus q squared plus a plus another 2a, that gives us 3a. And over here with the y coordinate, if we rearrange this to make p plus q the subject, we have that is equal to y over a, which I can substitute into my x coordinate over here. P plus q is y over a, and that is being squared plus 3a, and I'm doing all of this just to get x and y into the same equation. Then we have a y squared over a squared, x minus 3a, multiply everything by a once I've cancelled that, and we have y squared is equal to ax minus 3a squared, which is what they want if we just factorize out an a. And at the very last step, I'll turn this into little y and x to match exactly what they've given me in the question. So we've shown that the locus of R is indeed that equation. That was quite a long, involved example, and one of the important things to take from that is that these identities are very useful. So if you have something like p squared plus q squared, or p squared minus q squared, or p cubed plus q cubed, or p cubed minus q cubed, then have a think about whether there's another way you can write that in terms of brackets, squared or cubed, that will help you get something more useful for solving your problem. So a summary of the information again on the screen here, just noting that you could be asked questions from FP1 like we were just there. We had a question about a parabola. Just because it was an FP1, not FP3, doesn't mean it can't come up in the FP3 exam. And also, just a little note of this one here that was probably new to you, that this is a useful identity to have seen for solving questions like this. Problem-solving questions can be quite difficult, and my advice would be to do as many as you can, because the more of these you do, the more you will see little tricks like that when you struggle with them, and the more you see little tricks like this, the more you will see them in later questions, and you'll get something that you've kind of seen before, even if it's not exactly the same. For example, now you've seen this in this example. If you see a p cubed minus a q cubed in another question, hopefully, even if you don't remember exactly what it is straight away, it will trigger something in your mind that says, oh, I've seen something like this before. So although they can be quite difficult and quite long, my advice is do as many as you can, because they do usually get easier the more you do them. Lots of questions for you to practice these in exercise 2F of the textbook, but you can also now do the chapter 2 review exercise for the whole chapter, further coordinate systems. And maybe I'll see you for another chapter.